Okay, so this example, we're going to do finding the extreme values of a function on the given interval. So we have a cube root function. Exponent to the 1/3 is actually the cube root of whatever is in here, right? Remember the rider and the horsey. You have the rider goes on top and the horsey goes on the bottom. The rider's in the house and the horsey's outside, right? So the 1 is in the numerator and the 3 is in the denominator for your exponent on the base x minus 2 here. Okay? So this is the radical form, this is the rational exponent form. All right, now, to us, it's useful to have this in the rational exponent form because it's easier to take the derivative this way, so make sure you're able to convert. But let's go through finding the answer to this problem using the Clark way. So what's the Clark way say? It says that if I've got f to be some continuous function, which cube root, we're going to be continuous. You can take square roots of positives or negative. Cube roots of positives or negative numbers. You think about it like the cube root of -1 is negative. Well, what do you multiply by itself to get -1? 3 times -1 times -1 times -1. So cube root -1 is just -1. So negatives are okay here. It's square root where we run into trouble. So first thing I'm going to do, I'm going to compute the endpoints. Then I'm going to find all the critical numbers by setting the derivative equal to 0 or where it does not exist. And then third, I'm going to do f of c, so where c is each critical number that I found in step 2. And then the last thing, I'll take all those numbers from the endpoints and the critical values, and I'll see which one's the biggest, which one's the smallest, and then I will list out the absolute max and absolute min. So let's walk through this. First thing I do, I check the endpoints. So the first endpoint I'm going to check, I'm going to plug in 0. If I plug 0 in here, I have 0 minus 2 gets me -2 raised to the 1/3 power. This gets me -1.26 roughly. Okay. And so if I take the cube root of a negative, the negative automatically comes out here, and then I have the cube root of 2, which gets me that 1.26 approximation. All right, so that's that value there. So exact answer is negative cube root of 2. Now, the other endpoint is 3. So the endpoint 3, I'm going to plug 3 in here. So I have 3 minus 2 gets me 1. 1 cube root of 1 is just 1. Okay, so whenever I plug it, let's go 1, 2, 3. When I plug in 3, I output a 1 here. So look, remember, it's only on this interval here from 0 to 3, right? So we only care about the curve from here to here. So this is a closed interval. So it definitely looks like we're going to have a easy max and min here, absolute max and min. It looks like it's just going to be this value and this value, right? But we need to follow through with the Clark way steps. Clark way steps say we take the derivative of the function next to find our critical value. So the derivative here, how do I take the derivative of this function here? I take the 1/3, bring it out front, and I subtract 1 from 1/3, and that's going to get me the 1/3 here. And then if I subtract 1 from this, I have 1/3 minus 1 gets me -2/3. And I can simplify this. Okay, now chain rule, because this is not just a regular x inside. What's the derivative of x minus 2? Well, the derivative of x is 1, and the derivative of -2 is 0, so that's just 1. So chain rule, kind of easy there. All right, and so if I simplify this, negative exponent goes to the denominator, so that's 1/3, and then 1 over x minus 2 raised to the 2/3. Remember, rider and the horsey. The rider goes inside and the horsey goes outside the radical. So you got the rider on the inside and the horsey on the outside, just like that. So my final answer, written all nice and pretty, is this right here. Okay, simplified. Okay, And so where does this thing equal to 0 or does not exist? Is that even possible? The only way that a fraction is equal to 0, okay, is if the numerator is equal to 0. So I have to have like 0 over some number for it to equal 0, okay? If I have like a number over 0, that does not exist, okay? So is it possible for 1 to equal 0? No. So it's impossible for me to equal it to 0. However, I could have 0 in the denominator, which would be dividing by 0, which is a no-no. What number do I plug in for x that would get me 0 in here? Well, if I plug in 2, that's 2 minus 2, which is 0. 0 squared is 0. Cube root of 0 is still 0. So 2, x equal to 2 is a bad value. So x equal to 2 is one of my critical values, okay? Based off of our definition for finding critical values, set the derivative equals 0 or does not exist. And so I'm going to take that critical value, it's my only one, and I'm going to plug it in for g. And if I plug in 2 for g, what happens when I do 2 minus 2 to the 1/3? That's going to get me 0 to the 1/3, which happens to be 0, okay? And so where does 2 fall? 2 falls right in here. And so that, my friends, right now, we don't have the tools to determine if it's a relative max or min. But when you look at this with a picture, it definitely does not look like a relative max or min, okay? So, but in another section, we're going to get the tools that tells us how to determine if this would be a relative max or min, okay? And I'll allude to that more in the next example. Now, what does this tell us? Looking at our list of our 3, I have 0, I have negative cube root of 2, and then I have 1. So the biggest value is 1, okay? And that occurs at x equal to 3. I'm sorry, x equal to 0. Okay, so when x is equal to 0, I have an output. Oh, wait a second. What's going on here? Uh-oh. Made a typo here. All right, so g attains an absolute maximum. It's actually at 3. So this is an x value of 3 here. Better correct that on my notes. Make sure I don't do that again. All right. Okay, so this should be 3 here, because at 3 there's an absolute max of 1, and then it attains an absolute minimum value at x equal to 0 here. Okay, so at x equal to 0 there is where it's the absolute minimum value of negative cube root of 2. Okay, sorry about that little typo there. All right, h of x is equal to x squared times e to the x on negative 1 to 3. Now, first thing that I'm going to do with the Clark way is I'm going to compute the endpoints. What are my endpoints? Negative 1 and 3. So I've got my graph here. Negative 1 inputted for h. If I plug in negative 1 in here, I get negative 1 times negative 1, which is positive 1. Raised to e to the negative 1 is 1 over e. Okay, that gets me 1 over e for an answer there. If I plug in, so this output here is 1 over e, positive, right? And then the other input or endpoint is x equal to 3. So I'm going to plug in a x equal to 3 for h of x, so that's h of 3. And if I plug in 3, what's my output going to be? Well, that's going to be 3 squared times e to the 3. So that's 9e cubed. which is up there. Okay, so that number, whatever, right? I guess that would be, yikes, I don't even know what 9e cubed would be. So 9 times e second e cubed, right? Okay, so 180, that's pretty big. So that gets, this function right here gets really big really fast. Doesn't take long for it to get up like monster big, like 180, right? So that's a little misleading there. All right, so the y scale is vastly different than the x scale. All right, that's okay. That's part of it. Now, we're only considering values on -1 to 3. So -1 to 3 is only going to be on this part of the graph here. Okay. Hold on. Okay, so now what I'm going to do is I'm going to take the derivative. How do I take the derivative of a product? I use the product rule. So the product rule says the first times the derivative of the second. What's the derivative of e to the x? It's just e to the x. Plus the second, e to the x, times the derivative of first. What's the derivative of x squared? That's just 2x. Okay, I can simplify this. Both of these have an e to the x in it, so I'm going to factor an e to the x out, so that leaves an x squared plus 2x inside here, factoring an e to the x out. I can simplify this even more. Both of these have an x, so I'm going to pull an x out of that. And then if I pull an x out, I have an x left. And I pull an x out of this, I just have a 2 left. Okay? Now, what do I do when I'm finding the critical numbers? I set the derivative equal to 0 or where it does not exist. Guess what? This is transcendental times this polynomial here. E to the x is continuous everywhere. If you remember, exponential function is continuous everywhere, right? And then this polynomial, that quadratic, that's definitely continuous everywhere too, right? So that I think that quadratic looks something like that. Maybe roots here at 0 and -2, right? Okay. If not, don't worry about it. Just doing that off the fly. Now, what do I do? Well, I'm going to set each factor equal to 0 because I set this equal to 0, right? Factor theorem. So where does e to the x equal to 0? Well, remember the graph. The graph looks like this, right? Passes through at 0, 1. But guess what? Where does e to the f, that graph e to the x equal to 0? It actually never equals 0 for real numbers. Okay, only in the complex field can you get e to the x equal to 0. All right, but we're dealing with real variables here. So don't worry about that. This is never equal to 0, this exponential. So we don't have that as a scenario for an x value. And if you think about it, if you log both sides, if I did ln e to the x equals ln 0, well, that cancels. I get x equals ln of 0. If you try to type ln 0 in your calculator, I think your calculator is going to get mad at you. Overflow. Undefined, right? Okay, so we set this piece equal to 0. I'm going to set this piece equal to 0. That was easy to solve. So x equals 0 is another critical point. And then this one equal to 0. This problem, guys, this is a super tricky problem. Don't let this trick you up. Why is this so tricky? X equal to -2 is a critical number. But guess what? We do not care about x equal to -2 because our interval is from -1 to 3, okay? So you need to be careful on this, especially if you see like a test question like this. If you're outside the interval, one of your critical points are outside this interval here, I don't care about it. It doesn't matter to me anymore because this is outside the interval of numbers that we're considering, okay? We only care about numbers that are in this little box right here, okay? Everything outside of that is garbage. Nobody cares, okay? We only care about x values in this domain here. -2 falls outside of this interval, so get rid of it. Don't worry about it. So the only critical value we have is x equal to 0. So I'm going to plug in 0 for x for h. And then if I plug in 0, I get 0 squared times e to the 0, which is 0. Okay, so this right here looks like critical point here and here. So what is the biggest number? What is the smallest number in this list? Well, the absolute maximum is this big number right here with that 118 or whatever that number was. I don't even remember now. That's the biggest, right? Where did that occur at? That occurred at x equal to 3. Okay. Where's the smallest number? Well, 1 over e is small, but it's not smaller than 0. 1 over e, guys, I think 1 over e is like, let's see, I'm just going to do that. That's like 0.3678. I mean, that is tiny, right? But it's not smaller than 0. So this is actually the smallest value that is attained. It is the minimum, absolute minimum, and it occurs at x equal to 0. Okay, so you look at this graph here, you can see that there. Now, let's just think about this just for a second here. So we're done with this problem, but I want to just end this video on this idea here. At x equal to -2, okay? It looks like at -2 that we have a relative maximum. Wouldn't you say? That kind of looks like it's tipping out at a relative max. That's what it looks like to me. You know, maybe it is, maybe it's not. Now, we don't know yet. We don't have the tools yet to know if it's a relative maximum. But when I look at this problem, what do I notice? The slope of the tangent line on the left side of -2, it looks like the slope is positive. It looks like I have a positive slope over on the left side. When I look at the slope of the tangent line on the right side, what does it look like? It looks like the slopes are negative, right? It looks like the slopes are negative. So on one side I have positive slopes. On the other side I have negative slopes, okay? And then I've got this critical number separating the derivatives of positives and negative slopes, right? And so in section 3.3, we're actually going to be able to figure out a method, just like we had the Clark way for finding extreme values on a closed interval, okay? We're going to find a method on calculating the relative max and mins of functions without having to use our calculator, which is pretty cool. All right, so I'm going to